data today, everybody, is we're going to see that our data is so powerful and is so strong in how quickly it grows that we're going to have to condense it in both the x direction and the y direction. So both the x's and the y's will have to be logged. But when you go into a problem, you don't know that until you have first checked your linear. So you would go through here, and we got this for our linear. You're doing your labels, length and weight, length and residual weight. Here's your equation. So based on this information, is a linear model appropriate? It is not. A linear model is not appropriate, and the reason for that is because there is a pattern in this residual plot. Okay, so the linear model is not appropriate. So then we go to our next transformation that we know how to do, which is the exponential. And so that one is going to happen by keeping the x's still, your L1, but then condensing the y's and logging the y's. So we had that in our L4. So when you get the picture, I thought it's kind of weird, but it looked almost inverted at the one before. So we ended up having resid log W. Here's what the residual plot looked like. We did have a stronger R value, okay, but was an exponential model appropriate? And we say no again. So that's what's happened, is that we have found a linear model and an exponential model. The reason this one is still not appropriate is because there is a pattern in the residual plot. Therefore, an exponential model is not appropriate. Okay. So we go to the next thing. The next thing is this. It's the power model. Okay, so in the power model, we're going to use the log of x's. Now, where are your log of x's located? Good. They are located in your L3. We're going to be using the log of y's, and they are located in your L4. So when we graph this, what will be on my x-axis that I graph? Good. I'm going to do log of length. That's log of the x's, and the y-axis is going to be log of the weight. Okay, so I have the data in my calculator. For me to look at that picture, I'm going to go to my stat plot, and what lists do I look at? Good. The x list is your L3, and the y list is your L4. You zoom 9, and that looks a lot better. I can already tell that this one has potential. It looks a lot more flattened out than the other two, the linear and the exponential models. So I'm going to fill that in. Okay. So I want to look at the residual of that. I need to find the equation of that line. And that's the equation of the log 3 and the log 4. So, how am I going to find the equation of the log 3 and the log 4? Stat, over to calc, and then number 8, which is your lin reg. Good. You are wanting to find it for L3, comma, L4. And I enter. And so there we have the y-intercept is negative 0.0103. So predicted, what am I predicting here? My equation is about predicted, not just weight, log of weight. Very good. Predicted log of weight that's what the y variable is, equals negative 0.0103. Okay, and then the y, or the slope, was 3.02. Now, your x variable is what? It is the log of length, not just plain length. It's the condensed length. All right, very good. So, it looks like it has great potential. Let's confirm in the residual plot. By the way, the R value was 0.998. Okay, when we looked at that information in our calculator, we had our correlation coefficient, 0.998. Okay, so here we go. So here comes our residual plot. I have calculated the new equation. I haven't put my resids in yet, so I need to go do that. No. Okay, so there's old stuff. Okay, so how do I know that I'm going to get the correct stuff in L5? Because I know my calculator is thinking of that new equation of L3, L4. Okay, so I'm going to go and second stat, resids, enter, there they are. And so now I want to look at them. Now let's label this. What do you want? What's going to be on this horizontal axis? Okay, these are the predicted log lengths. No, that's not true. This is the log length axis along here. And on this is, very good, resid of the log weight. All right, so let's take a look at that. To take a look at that, go to my stat plot. The X list is remaining L3, and my residuals are in L5. So then I look at that. Here we go. Ta-da! And so that is what you got. So much better. This is nice scatter. We've had a very good R value, 0.998. Yes.
When I put in the residual for the L5 and the residual L4, is that like I'm just
So that's the same thing? Huh. Okay. If you had already calculated the equation of the line, I don't think that would be different. No. Right, correct. Good. Okay. Because it's going to do the residuals of the y that it's thinking of in its equation. So whatever you had resided or calculated for the y, it's going to do the resids of that. Okay, so then we're going to put that in there. We've got this. All right. So, is a power model appropriate? Yes. Okay, great. So we have gotten that accomplished. Now, I'm going to take a few minutes. I'm going to let you go through the assignment. There's 2 problems on the assignment. They do both need to go through the power model. Now, I want you to skip the little pieces that say, what's the equation and do a prediction. So let's hold off on this part of how to undo this log for a minute, and I'll come back to that after you've done a little work, and then we'll talk about that. So, do those power models. We'll come back and do this in a minute. Now, unfortunately, I boo-booed on this little piece right here. You have a squiggle, and you have a little B right here, and then you have a squiggle. Take that part out and put the big B here in front of your log X. Fix that on your notes. This is the back of the notes. You currently have a nice little squiggle arrow like that and a little exponent B. You need to take that out and put the B here in front of the log X. Log X. Huh? Okay. So now, let's first relate this to what you did yesterday. Yesterday, we had exponent form because our variable was in the exponent. Okay, so we ended up with this form. And our variable was right here in the exponent. Okay, Today, however, look at this difference. Predicted y is the same. This a is identical as the same way we computed it yesterday. It does come from the y-intercept of this equation by undoing the log of a. Okay, but look here. The variable is no longer an exponent. The variable in power model is the base of this exponent function here, okay, the base. And furthermore, this b value, you do not have to unlog it. It will be the real b that occurs in the equation you got. That's the two differences. So let me explain. Let me just do one quick little, here's mathematically why. If you have x to the b and you end up logging this, rules of log say this b comes down in front, and so you have b log x. So these two things are comparable. That's why we are going from this to x to the b. Okay, that's a little quick mathy thing if you want to know it. But otherwise, let's do this problem in our notes. Here is the equation that we just got above when we thought a power model is appropriate. Predicted log w equals negative 0.0103 plus 3.02 times the log of the length. Alright, so let's undo this log problem. This y-intercept is where the a value is derived. Okay, so remember to do this, I am saying log a equals negative 0.0103. And then how do I undo this log here? 10 to the negative 0.0103. And that's what a is. I have computed that value, and it is 0.977. Okay, now, I want you to consider unlogging this component here. Well, the unlogging process addresses your log of length. That's how you get your regular old length. Okay, so unlogging this gives you the regular length, and then this slope turns up into the exponent. So this still stays 3.02. Okay, because the log's energy basically was taking into transforming this length. You're not changing the b value. So in summary then, the final answer would be predicted, it's no longer logged anymore, so it's just predicted what? Weight, okay good, predicted weight equals the a value. And what is the base of this function? Length, very good. That variable is the base of the function, and the exponent is the previous slope, 3.02. Final thing that is crucial, you have to know what the heck this has just done for us. And so, final question is this. What equation, or what function, what points, what graph would this picture go through the points on? What graph would this picture go through the points on? Would it go through, do you think this is going to go through one of these up here? Do you think it's going to go through one of these on the first page? Okay, which one do you think it will go through? Ah, you think the original one, the L1, L2? So I have this data still in my calculator. Okay. Actually, let's go to the y equals. Here I have that equation that you just found, that power model equation. 0.977 times x to the 3.02. And you guys told me that that was supposed to fit L1 and L2, the original data. Let's see if that's correct. Do-do-do. So here we go. Let's see if our original data is what we found the equation for. And that's correct. Okay? So in summary, we compress the data twice, in the x direction, in the y direction. Then we found the unlogged equation that it is in the power model form, and this is the equation that matches the original data set. That was the ultimate goal, is to find what fits the original data. Okay? So then now you can go and unlog those problems and do the predictions on your papers.